And we're live. All right, ready? Here we go. All right, so octal and hex numbering systems, we would call that base 8 and base 16. Okay, these are two numbering systems used in computers and digital electronics. Basically, is a way to create bigger and better programs, right? This is a great example if we think about the history of video games, right? So back when I was a kid, you had things like Atari, okay, which was pretty basic, and then Nintendo came out. It was an 8-bit color system, which means it had a whopping 256 colors. This was like mind-blowing at the time, okay? Because before that, you had like Pac-Man, which had like 8 colors, okay? Which was a basic binary system, right? 8 bits in a byte. And then we moved up to hexadecimal, okay, with Super NES. And then eventually, PlayStation came out and blew everybody out of the water with 32-bit color. And then now you guys don't even know where you're at. Probably zillions of colors at this point, okay?
I think it's 16.7 different colors. 16.7 million different colors.
16.7 million different colors, right. Okay, so but it's also about computers being able to basically compress and decompress long strings of binary information in a more compact format, and that's really why octal and hex are a thing. We're also going to be learning about a couple of different ICs that are going to be using octal and hexadecimal systems, so that's why it's kind of important for us as well. Okay, so this is basically what I was just describing, except around video games and consoles. So basically, we're going to be able to go. We can already go from binary to decimal back and forth, right? And in a similar fashion, we're going to do the same thing with octal and with hex, except that instead of base 2 like binary, octal is going to be base 8, and hex is going to be base 16. Okay, wrapping your brain around hex is a little challenging for some folks, but I think that you'll get it. All right, this is a really nice slide to have. I may even capture this one and add it to the assignment just because I think it's useful. But basically, it's showing you the conversion between decimal, binary, octal, and hex. Okay. Take particular note of when we get down to 10 in decimal here, okay, that we start to see a change here, okay? So notice that we should be familiar with binary, right? Octal is going to look a little weird, right? Why do we have a 12 when really it means 10, okay? So in order to understand octal and hexadecimal, you've really got to stop thinking in terms of what does that number represent, but keep in mind that each individual space or each digit in a total number is really a placeholder for the possible value in that column or in that category. For example, when we're talking in decimal, right, we have the ones place, we have the tens place, right? So let me write a number, 735, okay? We've really got 5 ones, right? We've got 3 tens, and we've got 700s, right? Remember back in elementary school when you got to play with the blocks? We're not going to do that. But if you remember, okay, that's what you did, right? You had the little cubes, you had the sticks, and you had the big block. Did you guys do that? Yeah, I love that. Okay, anyway, so that's the basic idea. But when we're dealing in things like octal, right, we have that number 12, we have the ones place, and then we have the eights place, right? Mind-blowing, okay? We have the eights place. And if we went out one more digit, let me put another number out here, like 5. This would be, what, 8 times 8? 64? Okay. This would be the 64s place. Okay. So think about that digit as there are 5 64s, right? There's only 1 8 and there's 2 1s. Okay. So you really got to break up the number into those categories, just like we did with binary, right? Remember we did binary. We said we had 1s, we had 2s, 4, okay, 8, 16, and so on. And basically, we knew that if there was a 1 there, we counted that. If there was a 0, we didn't. Except now we can have more than 1 in each column, right? It can be more than a 1 or a 0. And so we just had to kind of multiply. All right? Hopefully that makes a little bit of sense, but we're going to do a few problems, and hopefully it'll ring true for you. Okay, so I'm going to scroll down past all this stuff because I don't like the system that they use. I prefer to do our train track system like we did for binary. Okay, so here we have a number 189 base 10. Okay, and we need to convert it to octal. Okay, base 8. So what I like to do again is draw out those train tracks. So just like we did, we've got 8 to the 0 would be 1. Let me do a double line here. Sorry, it's kind of hard to draw with the mouse. 8 to the 1 would be 8, correct? And as we just said, 8 to the 8 squared would be, somebody help me? 64. And let's do one more. I don't know this off the top of my head, so somebody use a calculator. 8 squared, or 8 cubed rather, would be what? 512? Okay. So we have the 512s placed. So in order to figure this out, let's work backwards, right? How many 64s can I get into 189? Well, we can definitely get 1. Can we get 2? How much would that be? 128. Okay, yeah, so we can get that in there. Can we get 3 in? Another 64 would be 80. No, 83. That's too much. Okay, but we can get 2 in. So we have 2 in the 64's place. Okay, that was 128, so we got to do some subtraction here. All right, 189 minus 128. All right, what do we get here? We got a 1, we got a 6, and we got a 0. Okay, 61 left over. All right, how many 8s can I get to 61 then? We know we were close because 64 was, we can get 8 of them in. So we can get 7 in. Okay, 7 times 8. What do we got there? 48? 56? Thank you. Okay, and then we have a remainder of 5. And that's going to be easy enough. We can get 5 in here. Okay, so our answer was 275. Here's a quick check, too, to see if you got the right answer. Since this is a smaller base system, the number should appear bigger, right? So if I'm going from base 10 down to base 8, then I should appear with a bigger valued number because the system is smaller. If we're going from 10 to base 16, right, this number is going to look smaller because the numbering system is bigger. I can hold more values per column. Does that make sense? I'm going to take your silence as a yes. All right, so let's move down, and here they go. And it looks like we got the answer. Okay. Okay, this is going the other way now. So if we're going to go backwards, it's the same idea. We're going to use that same scale, right? So I'm going to draw it out. Okay. All right, so we had the 1s place, we have 8s, and we have 64s. There's only 3 digits, so that's all we really need for this one. So there's 1 in the 64s place, so that's 64. There are 3 8s. What's 3 times 8? 24. So we get a 24 here because we have to multiply. There's 3 of these. And then there's 4 1s, so we add another 4. And what's our total? What was it, 134? No, 132? No. What do we got? 8, 88, 92. 92, and that's in base 10. Okay. And we nailed it. Okay. So, they show another method in here, but I really just prefer the train track here. I just think it's a little cleaner and easier. You can certainly do the division as they show, but you're really doing the same math. I just find this a more organized way to figure it out. Otherwise, you've got to put these numbers out, and then people often reverse them, and I find it more confusing. Okay? All right. Any questions on octal before we jump into hex? Then here we go. Okay. So basically the same idea, okay? We're going to set up brackets that increase by 16 each time. The big difference here with hexadecimal is that at a certain point, we have to use letters to represent numbers. Any ideas why? Anybody taking a guess? Yeah, there's only so many base 1 numbers, and we can only take up one slot in the number. So if I want to represent the number 11, let's say we have 11 in the 16s column, which is possible, right? 11 out of 16, but I can only use one character to represent that value. Well, I can't put 1 because people are going to think it's 1. I can't put 11 because people are going to think it's actually 2 different digits, right? So the alternative to that is then to use alpha characters to represent the higher double-digit values, okay? So basically, once we get to 9, 9 is fine, but when I need to say 10 in the 16 columns, that's going to be A. When I need to say 11, that's going to be B, okay? And it's going to keep going up like that until 15, right? So what do we got? A, B, C would be 12, D would be 13, E, so F is the highest that it can go. Why, do you ask? Why not 16? Isn't 16 the value, Mr. Kish? Don't forget about 0. Okay, so 15 possible, and we'd have to move over to the next column, right? If we had 16 of them, then that goes to the 16's place. All right, so let's do one. Same idea here, except let's make our train tracks. So we have 16 to the 0 is 1. 16 to the 1 is 16. 16 to the 2. Somebody punch in the values for me. It's a big one. What is it? 256? Really? I think it's bigger than that. I could be wrong. Yeah, 16 times 16. Okay. I guess it's the next one that jumps into the thousands. Sorry. 256. All right, let's do 16 to the 3rd just so we can see the big jump then. That's the one I was thinking of. What is it? 4,096. Okay. So those are bigger increments, so it's a little harder to wrap our brain around this one, but let's try. So how many, well, we can't fit this into 429, correct? Okay. Can we fit 256 in? Yes. Looks like only one time because twice would be over 500. Okay, so we got 1, and we got to do some subtraction. So 429 minus 256. Anybody already have the answer? 429. I'm going to use the calculator minus 256. 173 left. Okay, great. So then how many 16s can go into that? I'm going to divide it by 16. Okay, we can get 10 whole ones in there. So 10 here. All right, will get us 160. All right, and then we're left with 13. And that should be an easy one. We can get 13 in here. Okay. Here's the problem, though. So we've got 2 with double digits that we've got to reconcile. Okay. So the 1 is fine. What do we say represents 10 now? What letter? No. A represents 10, right? We go 7, 8, 9, and then when we have to get to double digits, okay, 10 is the first double digit value. So A, 13 then would be what? A, B, C, D would be 13. So the answer here is 1, A, D. Okay, that would be the hexadecimal answer there. Okay. Questions? Let that sink in for a second. Make sense? Kind of, sort of? I know it feels a little foreign, but. Okay, and there we go. Really important to make sure you're labeling your numbers, okay, because it's possible to have 429 in hex in space 16. So, make sure that you're labeling which one's the base 10 and which one's the base 16. Okay? All right, let's go the other way now. If we have a value in hex, let's go backwards, right? So again, I know we've got the 1's place, we've got the 16's place, we've got the 256 place. There's only 3 digits, so that's all we need right now. Okay, so we've got E, which is really equivalent to what? 14. We've got 2, which is equivalent to what? 2. And we've got B, which is equivalent to 11. Good. So to figure these out right now, we've got, well, these can kind of come down, I guess. We need one more category here. So now we've got to multiply. 14 times 1 is 14. 2 times 16, 32. And again, I'm going to bust out the calculator for this one. Okay, 2,816. Okay, and remember now we're just going to add all three of these values up. So plus 32 plus 14. The total value is 2,862. And don't forget to mark it as base 10. Okay. Good. Questions on that one? All right. And we nailed it again. Nice job. All right, so why does everyone take just a quick second, attempt to convert this on your own, just get a little scrap of paper or something. I'll give you a minute, and then I will solve it for you. Oh, that's my fault. All right, so I'm going to go ahead and start solving this one. You can just ignore me for a second if you're not quite done. So in the ones place here, I've got A, which again was going to be equivalent to 10. We had 5 in the 16th place, so 5 times 16 is going to be 80. Okay, and then finally 2, we would add those two together, and the total would be 90 base 10. All right, was everybody able to give that a quick shot? Yeah, how'd you do? No? Didn't get it? Okay. Well, because we've got to speak the language of computers. Yeah, so remember that A was in the ones place. A really has a decimal value of 10, so we would have had to do 10 times 1. Okay, 5 was in the 16s place, and so 5 times 16 would be 80. Okay, 80 plus 10 would be 90. Remember, if we had one more digit in this number, we'd have the 256 place out here. So it's all about multiplying what's in that column times whatever the weighted value of that column is. Okay. What do we have here? Hex to octal.
Oh, that's what we were doing. I think it was the octal, not the
Oh, was it supposed to be the octal, not the base 10? Yeah. Oh, my bad. I didn't read the question. Okay. Well,
just convert it from base 10 to octal.
Yeah, that's kind of what they did. They did base 10, and then they did base 10 to octal, which was a pain. So we were halfway there. All right. I'm going to jump over that because what I want to get to anyways is how to convert these values to binary. Okay. So let's take a look at one together first. So similar idea. Again, really what you need to do first is convert to base 10. So they convert octal to base 10, 90. And then they go through and basically do the binary conversion like we've done in the past, right? So you're going to do your other train tracks and kind of go about it that way, right? We've got the ones place, 2, 4, 8, 16, and so on. Okay. And you would have to, again, kind of divide out and figure that out. Okay. I would not do, I prefer not to do that style. Okay. I think this is going to be a more organized format for you. Okay. This is where the real gold is here, okay? So slide here, and then I think this is the end of it, and you'll be free to go, okay? So the best thing really is that if you can convert a number to binary, it's very easy to go from binary to hex or binary to octal, okay? Because really what you can just do is group a couple of binary numbers together, and then you can add up their individual values to convert them to octal. For example, we have this binary number here, okay? We have 0, 1, 0, 1, 1, 0, 1, okay? If we're converting to octal, basically 3 bits of binary here would add up to 8, right? We have the ones place, we have the twos place, and the 4. So the range would be from 0 to 7 or 8 possible digits, right? Including 0, okay? So by grouping 3 together, we can actually get our full range of the octal digit, okay? So here they are grouping the first 3. So we had basically a 0, we had a 1 in the twos place, and another 0, so that would be equivalent to the 2 here. Here we had 1, 1, 0, so we had a 1 place and a twos place. We add those up, and we get our 3. And then this had only something in the ones place. There were no, basically there's 2 zeros that aren't there, so it's only worth the value of 1. You can do the same thing going to hex, except you need a 4th digit, right? That would give us 4 bits, okay? And it would allow us to do the ones place, twos place, 4s, and the 8s place. Total of 0 to 15 values, okay? Again, that would represent one possible column in hexadecimal. So if we add these 4 up, we had a 2 and an 8. That gives us 10. 10 is represented by A, so they convert it to A. And then here we had a 1 and a 4. Okay, add those up, and that converts to 5. Okay? All right. So I'm going to stop the presentation there. I think they have another practice problem for you. But I'm sure everyone's ready to move on at this point. So, okay, I'm going to stop.